of our cold formed steel, we're going to talk about fixings, and this is the bit everybody forgets. People look at a rivet or a screw or a bolt, and they've got plenty of capacity. And they're forgetting that it's probably not the bolt, rivet, or screw which is the critical part, but the little bits of metal around it. Right. So here we're going back to MathCAD. And the reason we come to MathCAD is because there isn't a spreadsheet for it and there isn't software for it, and nobody's done it. And you can do it yourself. And the way you can understand what's going on, you can understand how these materials behave under load, is go through it. So it's worth doing it once. You don't have to do it on every project every time. You've got to build up your confidence. You've got to convince yourself that you know what you're doing, and you've got to be able to trust the software to do what you think it's doing. And you've got to know what that software is doing. And you'll only get that after you've used it for a year and tested it again and again and again and go, well, it doesn't make sense, or it does make sense. So we start with, we start with bolts. And there's a clause 5, which does bolts, rivets and screws, and it treats them all separately, but the approach is very similar. And so I'll go through it just for the sake of completion. And so sometimes you'll join these bits of metal with bolts. So it's the big sections, the warehouses, the workshops, they're joined with bolts. And we'll start with a 10mm bolt, which is half the size you'd use in a hot roll section normally. And the thickness. So thickness of material under the bolt head is 1.6mm. Thickness of the sheet not in contact with the bolt head is 0.55. These are very thin bits of metal, and they can tear relatively easily. In this case, we're using grade 300 steel for both, and you can have different grades for top and bottom. 0.55 is quite a typical thickness for cladding, as well as our insulated panels. You check the tear out. The tear from the top layer, 16. So it's just the end distance multiplied by thickness multiplied by the ultimate capacity of the steel. So you get the minimum of those, and your tear out is 3.93 kilonewtons. Sounds quite a lot. Now, the net section tension in the connected part is about the space between the holes. So when you think about connection failure, you have to think about what elements will fail. The obvious thing that will fail is the bolt. Well, the bolt is mighty strong. It's not going to be that one that's failing. Okay, you've got thin bits of metal. That's the bit that's likely to fail. Well, which bit? How's it going to fail? Well, there are a number of ways. You could tear the end off it, or a chunk of metal could tear off in between. So we look at the net tension and we derive that tension capacity. So it's really, they call it tension, but it's actually a tension in the metal due to the shearing in the bolts. More likely it's bearing. Now there are two checks. Now the holes in your light gauge steel will yield long before an ultimate failure. Now I think that's a failure, and it's a failure because it's a serviceability limit state. If your holes enlarge in your connections on light gauge steel, and that light gauge steel happens to be your cladding, your weather envelope, your cladding is going to leak. Remember, rule number 1, keep the water out. But if you ignore that, you can get quite a reasonably high figure for your bearing capacity. If you limit the bolt hole deformation, you get a much smaller capacity based on that. A quick check on the bolts in shear. So we've got, in this case, grade 4.6, because we don't really need any higher. We've got section areas, depending on what we're doing with it. And we get out a design shear capacity of 10, which is way above what we need. Quick check on the bolts in tension, again, 18, above what we need, but we need to check the combination. you're applying tension and shear to the bolt at the same time. So the code tells you what's the squares and add them together, and that's your utilization factor. If it's less than 1.1, you're good to go on that. Oh, now move on to screws. Go to the screw capacity, and it's a similar approach, and it's quite common to join light gauge steel together with screws. These are tech screws. They're self-drilling, self-tapping screws. And if you're using them in cladding, they'll have a rubber washer on them or a neoprene washer on them to keep them watertight. Typical size is 14 gauge. That's 6.3 millimeters in diameter. We've got a different metal. So our very thin cladding is 0.55 millimeters thick, and the purlin in this case is 3 millimeters thick. There are our strengths, our yield strength and our ultimate tensile strength for both of those steel components. Again, we check the tension in the connected part, gives us a nice large value, in this case 2. Look at the tilting and hole bearing, and we end up with a value of 1.93 kilonewtons. So that is because your screw is in shear and you're bearing against a hole in there. And so your bearing can be often the critical element because you're looking at a very thin piece of metal. Check on the tear out compared to the end distance, and even at 20 millimeters edge distance, you've got plenty of capacity. Check on the screws in tension. So in some cases, you're going to be putting these screws both in tension and shear, depending on the applied load. So if you can imagine wind on a roof, it wants to pull the sheet off the roof, which puts the screw into tension. Because in other ways, your screw is in shear, depending on how it's done. So if it's wall cladding and you've got gravity loads on it, your biggest load is probably going to be in shear. But look at screws in tension. Now there's 2 aspects you need to look at. One is the pull out and the other is the pull over. Pull out means your threads are pulling out of the material underneath, i.e. the purlin. The purlin metal is failing. The pull over means your top skin, your very thin bit of cladding, is peeling over the top of your screw head. And even your washer, so that's pull over. And given that we've got screw diameter of 6.3 millimeters, and we've got a screw head of 12.6, we've got an effective pull over diameter of 12.6. That gives us a nominal pull out capacity of 7.71 and a pull over capacity of 4.2. Apply your strength reduction factor, and the design tension capacity of that is 2. So your factor of safety is quite high in light gauge steel connections. It's basically 2. Strength reduction factors are 0.5 or 0.6 or 0.65. They're all small reduction factors, much smaller than you'd use in hot rolled steel. There's a special section if you're using a top hat. There's another check to do. And then you check the combined shear and pull over, and then you check the combined shear and pull out. Okay, and shear and tension, not normally the issue, but if you've got the combined applied shear and applied tension, check them together. And this is particular to the capacity of the screw. The capacity of the screw is often done by testing, and manufacturers of those screws will tell you the capacity. Unfortunately, screws are not really standardized. They're kind of standardized in the sense of the diameter and the gauge, but the material can vary, and different screw manufacturers will give you different capacities depending on their testing regime. Finally, we get on to rivets, and this is very common for joining 2 very thin bits of metal, whether it's less than 1 millimeter thick. Now, these are not the old-fashioned hot-driven rivets that we used to use in big steel construction. These are the tiny little rivets, also known as pop rivets or blind rivets. And a typical large rivet is only 4.8 millimeters in diameter. So basically you insert your pot rivet, pull the lever, and it squeezes them together. It's a clamping action in there. And similarly with bolts and screws, there's a minimum forces depending on how the force is applied. So you need to check the capacities in each. So again, check the tension in the capacity of the connected part. And tilting and hole bearing can often be the governing factor. In this case, it probably is, because there's a number of formulae to go down until you finally get to the 0.61, depending on the relative thickness of the top and bottom sheets that you're connected. If you're limited by end thickness, even as low as 10 millimeters. The other thing is you're joining thin bits metal to small sections usually, and your channel is often only 30 or 40 mil thick, so your end distances can be quite small as well. So end distance can be an issue. The shear, you check your shear capacity. This is the tested value that the manufacturers have given you. Apply a factor of safety on it, or your strength reduction factor, to get your capacity of the rivet in shear. So this is the typical table for the different shear and axial tension capacities of your rivets, different styles. They're often what they call moly, which is a nickel copper steel alloy. That's the common one. You've often got stainless steel is another alternative, for aluminium. If you're joining aluminium sections, then you probably want to use aluminium rivets, and they have a capacity of their own. And there's yet another standard to look at. That's ASN ZS 1664, and that goes through a very similar process to 4600 in terms of capacity of rivets, screws, and bolts in aluminium structures. Okay. And the little pig has appeared again, and that means you can see more information about that on the YouTube channel, and also available through the website. I'm sure you've remembered what the website is, the YouTube channel is. So at the end of the day, I want you to go onto the YouTube channel and subscribe to the channel, share the show with your friends, and hit that like button. You can make me an influencer. I will be a YouTuber. Yes, I will. I'm an accidental YouTuber because I was asked to do CPD webinars because we're in lockdown. And I said, I'll do it if I can record them and put them on YouTube. And it's a good way of doing it. I now don't have to repeat them. I can just say they're on there, because every time you get new graduates, it's, oh, can you do these? Okay. And if the CPD seminars are 1 to 31. Unfortunately, I didn't record the first, but if I get sufficient demand, I'll re-record number 1. A reminder of the standards, NASH standard. These are freely available to download from the NASH website. So you can Google those. This is from the New Zealand version. There is an Australian version of NASH. They're not so free and easy. They make you pay for their materials. And if you're getting into light gauge steel, it might be worth joining or paying for it, because they present you with things like this. So rather than delving into all the MathCAD I've just shown you, you can pick it out of a table, and they've got tables for screws, rivets, and bolts. But unfortunately, it's a limited range of material strengths, and a limited range of material thicknesses. And so if it doesn't fall into that range, you need to resort to the MathCAD again, or do it by hand on pencil and paper, because there's probably not a spreadsheet for it unless you write it yourself. One day I will do this. This is the matrix. So to create a table like this, you can use MathCAD. I don't have time to go through the whole thing again, but you can generate Excel. MathCAD can generate Excel, and MathCAD can read Excel. So safe load tables that manufacturers often produce are often produced in Excel, and it's very easy to make a mistake in Excel and having to start all over again. Whereas if what you're driven by is the equations, and your equations are written in a form that humans can understand, then off you go click a change, and you can reproduce the files again. So you can generate these tables using matrices in MathCAD. Actually, I can't show you that because it's an advanced feature. You need the Prime Edition, the paid-for version of MathCAD to show that. And I've not connected to the server for that. This is what the table looks like for each of the thicknesses. So you'll notice that the Nash Australian version doesn't go down to the point, the very small thicknesses for the lower strengths in there. That's a reminder of the reference. That's our standard NZS 4600. Now, I've just noticed, of course, the current version is 2018. That's not the one that's endorsed by the New Zealand Building Code, and that's another issue. There's a hierarchy of standards and documents in New Zealand, and right at the top is the Building Act. Underneath that is the Building Code, and the Building Code refers to New Zealand standards, and they obviously don't talk to each other because there are many, many standards that are now out of date, which are the reference standard, and this is one of them. The reference standard from the New Zealand Building Code is the 2005 edition of this code at 4600. God knows what's the difference. There are slight differences in the two. Similarly with earthquake loading, they're still referring to the previous one. Wind loading, they're still referring to the previous one. In the very latest 2025 edition of the New Zealand Building Code is still looking at the 2004 edition of earthquake loading. Yeah, there are some subtle differences in that one. I can't see much difference between the two, but I've not studied the two in great detail. That comes neatly with 5 minutes to go for questions.